I know what to do now. I can cut off the end of that. As long as I start again, I can cut the end off that one and plug it down to the start.
Just stick it together.
Right, the more field lines, the greater the strength of the magnet. The magnet on the right is going to be stronger because it's got more magnetic field lines. A reminder that the magnetic field goes from north to south. So if you're drawing a magnetic field, you must include the arrows going from north to south in a bar magnet. You could use a plotting compass to find the magnetic field of a bar magnet. You bring the plotting compass close to the bar magnet. You draw an arrow either where the tip is pointing or where the tail is pointing, depending on which side you put it onto.
So north is blue.
You what?
Is north blue?
No. North is north, south is south. And our magnets, no. I know. Our magnets aren't very good. They can come apart and they can swip around. All you have to know is that there is a North Pole and a South Pole. And if you use a compass to go around it, then you'll be able to figure out the size of the magnetic field. I'm whittering a little bit because I got distracted by the question and also distracted by what's going on over there. Are you okay? Goody. So, compass, magnet, draw a little dot on the tip of the compass, move the compass so that the tail is touching the little dot, and then repeat. That'll find you the shape of the magnetic field. The Earth has got a magnetic field. This is geographic north, magnetic south. This is geographic south, magnetic north. The Earth has got a magnetic field because it's got an iron core inside, a revolving iron core, makes a magnetic field. The compass is attracted to the magnetic field, which is why we know the Earth has got a magnetic core. Right-hand rule, the direction of the electrons is that direction, which means the direction of the magnetic field is going to be the direction that your fingers are pointing. When current flows through a long thin conductor, a magnetic field is produced. The field is circular, perpendicular to the wire. All that means is that the magnetic field goes around the wire. Circular, perpendicular just means it goes around. If you change the direction of the current, according to the right-hand rule, you will change the direction of the magnetic field. We need to know that for transformers later on. The larger the current, or the closer you are to the wire, the stronger the magnetic field. If I get a coil of wire, if I get a wire and I coil it up, I make something called a solenoid. A solenoid has got a strong uniform magnetic field line inside the coil and almost nothing outside the coil. Weaker field outside, stronger field inside. How do I know this? There are more field lines in the middle of the solenoid. A current-carrying conductor that is placed near a magnetic field. I don't think we've done this yet in lesson, have we? No, we'll talk about it now. If I put a current-carrying conductor into a magnetic field, it will make its own magnetic field. So there's a wire, the current's going that direction, making its own magnetic field. If I put that magnetic field, that long conductor, into another magnetic field, then there will be an attraction or a repulsion. I can make my wire move. If I do it in a very clever way by putting a current through a coil and putting that coil into a magnetic field, I can make it spin. That's a motor. This is the diode. Help me out here. No. Dynamo. Thank you. That took a long time, didn't it? You what? Yeah. Can't believe I forgot it. Why is it that attraction happens in unlike poles and repulsion happens in like poles? Attraction is due to the field lines lining up in the same direction. Here, my north and south magnetic fields are going in the same direction. There, they're going in the opposite direction, so they push against each other. Attraction, repulsion. Attraction, repulsion. Okay? Left-hand rule, we'll do that. We'll do that tomorrow. Actually, we'll do that next topic. When you put a magnetic material into a coil of wire, you get an induced potential difference. Magnet traveling through a coil is going to induce a potential difference. Because it induces a potential difference, it will induce a current. When you put your magnet through a coil of wire, you will get a current. If you keep a magnet still inside, there will be no current. If you move it faster, you'll get more current. If you put a stronger magnet in, you'll get more current. If you put in more coils, you'll get more current. The magnetic field and the electrical field lines interact. The current that's induced acts against the change, trying to return things to the way that it was. That's why you get this, this force in between. Here's a transformer. Inside my transformer, you need to have alternating current so that you can cause an alternating magnetic field inside the coil of wire solenoid in the primary coil. When you change the direction of the alternating current, you will change the direction of the magnetic field. Like, you just got to do. There we go. Pardon me?
Is it so it's an alternate magnetic field?
Alternating magnetic field. Yeah, the magnetic field is produced and it follows the right-hand rule. When I change the direction of the current, I will change the direction of the magnetic field. I've got an alternating magnetic field now traveling through my secondary coil. When my magnetic field goes through my secondary coil, it will interact with the electrical field lines, causing an induced potential difference, an induced alternating voltage, an induced alternating current. This whole thing is called the generator effect. If I was to have more coils in one winding and fewer coils in the second winding, I would change the voltage that is in my transformer. This is an example of a step-down transformer. I've got my AC power supply and I've got some primary windings. I've got fewer windings in the secondary coil, which means my voltage is going to step down. My voltage is going to decrease. When my voltage decreases, my current is going to increase. This is because we assume the power to be 100% efficient, the transformer to be 100% efficient, and for the power not to change. P1 is equal to P2. I times V is equal to IV, I times V. So we can do what's called our Vpip equation. High current means high resistance because negative electrons collide with the positive ions in the wire, causing the positive ions to get an increase in kinetic energy. Increased kinetic energy means increased thermal energy. Increased thermal energy means you've got a less efficient transport between point and point B, point A and point B. We can use the equation P is equal to I squared times R to demonstrate that, to show that the amount of power is being lost is very, very large. If I reduce the current going through my pylons, if the current goes down, then I will have less wasted energy. Higher voltage doesn't affect anything. If we increase the potential difference through the power lines, this will decrease the current. When we decrease the current, then we're going to have less wasted energy. Transmission is more efficient. That tells me I'm late for something. Et voilà, c'est là. That's it, done.